Okay, so what if the biggest hurdle, the thing separating an AI agent that looks amazing in a demo from one that actually works reliably in production? What if it's not better prompts?
Or even like a bigger, more powerful model.
Exactly. What if it's a single skill, something fundamental, but often kind of overlooked?
Okay, I'm intrigued. Sounds like we're digging into something that's causing a lot of teams some real headaches. What is this skill?
We are talking about context engineering.
Hmm.
Andrej Karpathy, he nails it, calls it the delicate art and science of filling the context window with just the right information for the next step.
Ah,
And if you think about it, it's actually pretty intuitive. Imagine your LLM, that's like the CPU of your AI system,
right.
and its context window, that's the RAM.
Okay, yeah.
And just like RAM, that context window, well, it has hard limits, capacity limits you have to manage really, really carefully.
That analogy clicks immediately. It really frames it as an architectural challenge, doesn't it? It's not just what the AI can do.
It's what it can hold in its mind at any one time.
Exactly, that capacity constraint.
Precisely. So look, if you're trying to build AI agents that go beyond, simple one-shot tasks, if you want them to handle complex, long-running workflows.
Like a serious debugging jobs or
Yeah.
maybe multi-stage research project.
Yeah, exactly, that kind of thing. Then this deep dive is definitely for you. We're going to lay out basically a complete framework.
Okay.
By the end, you'll get why so many agent projects just hit a wall, like a scaling wall they can't seem to get past.
And hopefully how to actually design for context management right from the start.
Yes. And we'll even show you specific techniques, the kind used in production systems you might know, like Claude Code or ChatGPT.
Right. So our mission today really is to understand why context engineering is becoming, well, maybe the #1 job for engineers building serious AI agents.
It really feels like it is.
We'll dig into the 4 main strategies people are using: write, select, compress, and isolate.
And critically, show how you can actually implement them. Real examples, practical takeaways.
So you can apply this stuff to your own projects.
Okay, so mission clear. Let's tackle the big question first.
Yeah.
Why is this such a big deal? Why this context crisis, as we're calling it?
Well, the core problem is that agents, when they're doing these longer tasks, they hit a fundamental scaling problem.
Right.
Every single turn. An instruction, a tool call gets made, there's feedback coming back, the agent does some reasoning, all of that. It accumulates tokens.
Right, just adding up, adding up.
And adding up fast. They quickly bump up against those context limits we talked about.
Which leads to things going wrong.
Seriously wrong.
Yeah.
It leads to some really nasty failure modes. Drew Brunig actually documented these really well.
I've definitely seen this happen. Agents just go off the rails, suddenly forget what they were doing or start talking nonsense. Is that what these failure modes feel like?
Absolutely. First, you've got context poisoning.
Okay.
That's when, like, a hallucination or just some wrong piece of information gets into the context,
Right.
and then it corrupts everything that comes after. The agent starts building its reasoning on, well, a faulty foundation.
Right. Garbage in, garbage out, but amplified.
Exactly. Then there's context distraction. This is simpler, maybe. The model just gets overwhelmed. Too much information.
It loses focus.
Yeah, it can't see the forest for the trees, basically, like trying to work with someone shouting random facts at you constantly.
And it gets worse, right?
Yeah.
I've heard of agents getting confused by stuff that seems harmless.
That's context confusing.
Yeah.
Information that seems irrelevant, maybe superfluous context, it can subtly nudge the responses in really weird, unexpected directions.
Leading to bizarre outputs.
Totally bizarre. And finally, maybe the worst for logical tasks is context clash.
Okay, what's that?
That's when different parts of the context actually contradict each other.
Oh, wow.
And the agent just freezes or flips a coin or just doesn't know what to believe or prioritize. It's a nightmare if you need reliability.
I can absolutely imagine. It makes me think of that Anthropic example with their multi-agent researcher.
Yeah, that was a stark one.
They found that once the conversations got past, 200,000 tokens?
Something like that, yeah. A huge amount, but still finite.
The context just got chalked off, brutal truncation.
Yeah.
And the agent literally lost its entire plan. Just gone.
Right. A production system just falling apart because the conversation history got too long.
That's the brutal scaling math right there.
It is. Agent interactions, they can easily go for hundreds of turns. And each turn isn't simple. It's instructions, tool calls, interpreting results, the agent reasoning.
Think about a deep debugging session or a complex research project.
Yeah, those tasks can, and they often will, blow right past any reasonable context window limit, and then your agent just becomes unreliable, useless even.
It's really no wonder then that cognition AI, they're really pushing the envelope on autonomous agents.
Yeah, they're doing some amazing work.
They basically call context engineering the #1 job for people building agents. They're saying, look, it's not about fiddling with prompts forever. It's about the fundamental architecture, designing for coherent reasoning at scale.
That's a huge mindset shift for a lot of people.
It really is. But, okay, here's the good news, right?
Yeah, there is good news.
The teams building these truly production-grade agents, they haven't just whined about the problem. They've developed systematic ways to tackle it.
Exactly. They've built strategies, and we're going to walk you through the 4 core strategies they're using to solve this context mess head on.
Okay, strategy 1. With the crisis clear, how do the top teams start fixing this? Well, they give their agents something very human, external memory.
Ah, right.
This is the first strategy.
Well,
Cleverly writing context, saving information outside the context window so you can get it back later.
the simplest way to do this is using scratch pads.
Like taking notes.
Exactly like a human taking notes, jotting down ideas, intermediate steps, plans, while you're solving something complex.
You mentioned Anthropic's lead researcher doing this.
Yeah, explicitly. It saves its current plan to a dedicated memory area. Why? Because it knows the context might get truncated if it goes over that 200K token limit.
So it's being proactive,
Yeah,
preventing that catastrophic failure.
precisely. It's a safeguard.
That makes a ton of sense.
Yeah.
So how do you actually set up these scratch pads? Are there different ways?
Yeah, a couple of main approaches. You can have tool-based scratch pads. The agent literally uses a tool like a write to file or save TUD function.
Okay, straightforward.
Yeah, simple, effective. Or for maybe finer control, you can use state-based scratch pads.
How did that work?
Information gets stored directly inside the agent's runtime state object, like internal variables. This lets you control exactly which bits of that scratch pad are visible to the LLM at any given step.
More granular control, okay. But
Yeah.
scratch pads feel very in the moment,
Mm.
session specific. For truly smart agents, don't you need memory that lasts longer across sessions?
Absolutely. That's a whole different level of challenge. This is where memory systems get much more sophisticated. We're seeing ideas from really groundbreaking research, like the reflection paper,
Oh yeah, self-reflection from memory.
to create reusable memories from successes and failures. And also generative agents, which synthesize memories from lots of past interactions. These ideas are now being refined and actually used in production systems.
That's fascinating. So systems like ChatGPT or Cursor or Windsurf, they're automatically building up long-term memories based on how you interact with them.
Yeah, they're learning about you, about the project over time.
What kinds of memories are we talking about? Is it all just one big blob of text?
No, not at all. It's helpful to break agent memory down into maybe 3 categories. First, episodic memories.
Okay.
These are specific examples of successful past behaviors. Think of them like few-shot examples, but ones the agent learns and updates itself based on its own experience. It's learning from its wins.
Right. Last time I did X, it worked well in situation Y.
Exactly.
Yeah.
Then you have procedural memories. These are more like evolving instructions, rules, maybe best practices.
Oh, like an adaptive coding style guide. The agent learns your preferred way to format code over time.
Precisely that kind of thing. Or maybe rules for interacting with a specific API it's learned.
And the third type.
Semantic memories. These are facts and relationships. Think of it like a growing knowledge base. Facts about the code base structure, project requirements, maybe even just general world knowledge relevant to the task.
Okay, episodic, procedural, semantic. But the real trick must be the quality of these memories, right? I mean, if the agent remembers something wrong.
It could be way worse than not remembering it at all.
Yeah.
You've hit the absolute critical point. Bad memories are worse than no memories. And here's something maybe surprising. Just doing generic summarization to create these memories often fails
Why that?
because it loses crucial nuances. Details that seem small but are actually vital for the agent's future reasoning. That's why teams like Cognition AI, they're actually investing in fine-tuning models specifically for memory synthesis and compression.
So not just using off-the-shelf summarization.
No, they need models that understand what's important for an agent's thought process, not just what makes a short summary. They need to remember the right things accurately.
Okay, so for someone starting out building an agent,
Yeah.
what's a practical way to approach this memory stuff?
I'd say start simple. Definitely implement scratch pads for that immediate within-session context. Get that working first.
Makes sense.
Then, as your agent gets more complex, start layering in the other types. Episodic for learning from success, procedural for rules, semantic for facts. Build the infrastructure for memory proactively. Don't wait until you're drowning in context.
Yeah, plan for it. For you, listening, think about this. What kind of information do you wish AI agents could remember across sessions to be better collaborators for you?
For me, it's often the why, the context behind my request, not just the task itself.
Oh, that's a good one. Or maybe remembering preferences across different projects without me having to repeat them.
Exactly. That kind of continuity.
That meta context, yeah. Remembering the spirit of the work, not just the letter of the instruction. Okay, so we've covered writing stuff down, but just having it written down isn't enough, right?
Oh.
You need to find the right stuff when you need it.
Precisely. Which brings us to strategy number 2, selecting context. This is about intelligently pulling relevant information back into that limited context window, but only when it's actually needed. This is where RGER retrieval augmented generation really intersects with agent architecture.
Okay. So for Scratchpad, selection seems fairly easy.
Yeah, relatively. If it's tool-based, the agent just calls a read function. If it's state-based, you have explicit control over what parts of the state you expose.
But for those long-term memories, potentially thousands of them, finding the right one sounds hard.
It is. It's a major challenge. Now, for very narrow, specific domains, simple tricks can work okay. Claude Code, for example, uses a cleolati.md file. It's like a dedicated, always loaded instruction sheet. And systems like Cursor or Windsurf might use specific rule files that act like always-on procedural memories for coding tasks. But these are for focused use cases.
So anything broader, you're going to need more firepower.
Definitely. For larger, more diverse memory collections, episodic, semantic, you absolutely need semantic search.
Meaning using embeddings.
Typically, yeah.
Yeah.
Using embeddings to find memories that are conceptually similar to the current situation, or sometimes knowledge graphs to retrieve info based on learned relationships between entities.
But this selection process, it can go wrong too, can't it? I remember Simon Willison's example with ChatGPT.
Oh yeah, the location injection. That was wild.
He described how the system unexpectedly pulled his physical location from his memory somewhere and just stuffed it into an image generation prompt he was making.
Yeah, and users felt like their context window, quote, no longer belonged to them.
That's a really unsettling feeling. It really highlights how critical precise selection is.
Yeah.
You don't want random, irrelevant stuff bleeding in.
It shows how context can become a liability if it's not managed meticulously. And it's not just memories. Tool selection has similar issues.
How so?
Well, if an agent has access to dozens, maybe hundreds of tools, and their descriptions are kind of vague or overlapping.
It gets confused about which one to use.
Exactly. It might pick a suboptimal tool or just get paralyzed, but there's good research showing that applying RAG principles to the tool descriptions themselves.
You mean retrieving only the most relevant tools for the current step?
Yes. That can improve tool selection accuracy by like 3x. It helps the agent focus.
That's a big jump. But okay, let's talk really complex domains, like retrieving knowledge from huge code bases. That must be another level of hard.
Oh, it absolutely is. The Windsurf team had a great quote. Indexing code does not equal context retrieval. Just having an index isn't enough.
So what do they do?
Their system uses a whole pipeline. It involves abstract syntax tree parsing to understand code structure, semantic chunking, embedding search, but also like old school grep and file searching, knowledge graph lookups, and then, crucially, a re-ranking stage at the end.
Wow, so it's not one single technique.
Not at all. That's the key insight, really, from all the production teams. There's no single silver bullet for retrieval.
It's more about combining different methods.
Exactly. You need hybrid approaches, embedding similarity for concepts, keyword search for exact matches, maybe knowledge graphs for relationships, and definitely that re-ranking layer to bring the absolute best results to the top, given the immediate task.
So production systems layer these, like start fast and cheap, then get more sophisticated.
Typically, yeah. Start with fast heuristics, maybe keyword matches, then apply the more expensive semantic search, and finally, use a model to re-rank the top candidates based on the very specific current context. Get that precision.
For you listening, what's your experience been with RAG systems? Do they always get you what you need? Where do you feel the gaps are between, say, retrieval accuracy and what you, as a user, actually needed in that moment?
That's a great question. For me, sometimes it feels like RAG gets you a relevant document, maybe.
Yeah, find something related.
But not always the exact paragraph or the precise angle or the specific fact you needed for this point in the conversation, that last mile of relevance.
Exactly. The last mile problem, which actually leads us perfectly into our third strategy, compressing context.
Right, because sometimes even the right information is just too much information for the window.
So compression is about keeping the essential stuff, but ditching the redundancy,
Yeah.
getting the signal, losing the noise. It sounds like information theory meets agent design,
That's a good way to put it. And the most common approach here is probably context summarization.
like that Claude Code auto-compact feature you mentioned.
Exactly. That's a prime example. When the conversation hits, say, 95% of the context capacity, Claude Code automatically generates a summary of the conversation so far.
Buys some breathing room.
Yeah, makes space for new turns while trying to retain the gist of what happened before.
But just like with memory creation, summarization can't be one size fits all, can it? How are teams doing this in more nuanced ways?
Well, there are different strategies. You can do recursive summarization, summarize chunks of the conversation, then summarize those summaries. That scales really well for extremely long interactions.
Like a pyramid scheme for summaries.
Kinda, yeah. Or there's hierarchical summarization. You maintain multiple summaries at different levels of detail simultaneously. Anthropic uses this for monitoring complex tasks. And then there's selective summarization. You might decide to only summarize certain types of interactions, like keep the tool calls and results, but summarize away the agent's internal step-by-step reasoning, perhaps.
But the big risk, again, is losing something important, right?
Right.
Losing that critical nuance during summarization.
Absolutely. That's the core tension. Generic off-the-shelf summarization models can definitely flatten things out too much. They might lose the subtle point that's crucial for the next decision.
And that brings us back to cognition AI.
Exactly. This is why they fine-tuned models specifically for agent trajectory compression. They needed models that understood what details are actually essential for an agent's ongoing reasoning, not just for a human-readable summary.
It's about distilling the essence needed for the machine's next step.
Precisely.
So when do you actually do the summarizing? Are there strategic moments?
Yeah, you have choices. You could summarize at regular intervals, say every 10 turns, or trigger it when the context hits a certain percentage fill, like 90%.
Okay.
It's also often smart to summarize after a distinct subtask is completed, or, very importantly, summarize before handing off context between agents in a multi-agent system. Clean up the state before passing the baton.
And what about those really verbose things like search results? You mentioned them earlier.
Yeah, post-processing tool calls, especially things like web search, is super important. Those can return thousands of tokens.
Right.
Smart agents will immediately summarize those results, pulling out only the bits directly relevant to the task at hand, and discard the rest before it even pollutes the main context history.
That's clever. Keep the context clean. Okay, so summarization uses an LLM. What if you want something faster or cheaper? Is there an alternative to LLM-based compression?
Yep, there is. It's often called context trimming or pruning.
Trimming.
Yeah, instead of generating a new summary with an LLM, you use rules or heuristics to just cut things out.
Like what?
Simplest is just removing the oldest messages once you hit a limit, FIFO first in, first out. Or you could filter out tool calls that seem less relevant based on some scoring, or identify and remove redundant information.
Yeah, more rule-based.
Rule-based or even learned. There's research like the Provence paper showing you can actually train models to be effective context pruners, learning what's safe to remove, and they can outperform simple heuristics.
Interesting. So whether summarizing or trimming, the core idea is preserve the signal relevant to the task and ruthlessly cut the noise.
Exactly. And doing that well requires really understanding your agent's workflow. What information does it actually need for future steps?
An advanced pattern here for really complex stuff. Could you maintain multiple compression levels at once?
Absolutely. That's a sophisticated approach. You might keep a highly detailed context for the immediate past, a medium detail summary for the recent history, and a very high-level summary for stuff that happened way earlier. Gives the agent different zoom levels on its own past.
That sounds powerful. Okay, listener, question for you. How do you currently handle super long conversations in your AI systems? Do you summarize? Just chop things off, truncate, or maybe just start over when it gets too messy?
I suspect a lot of people default to truncation, maybe. It's the simplest, but feels brutal.
It does feel brutal. That tiered summarization idea sounds much more elegant.
It maintains continuity better. Which actually leads us to the fourth and final strategy. This one is less about fiddling within the context window and more about the overall architecture, isolating context.
Ah, so building the system differently from the ground up.
Exactly. It's about splitting information across different components to manage complexity, building the agent system so context management is inherent in its design.
And multi-agent systems seem like the most obvious way to do this, right? Especially with things like OpenAI's Swarm library getting attention.
They are definitely the most popular approach right now. Swarm, for instance, is explicitly built around separation of concerns.
Really?
Each agent in the swarm handles a specific subtask. It has its own dedicated tools, its own instructions, and crucially, its own focused, isolated context window. Context is naturally separated by agent boundaries.
And we know this works at scale, that Anthropic multi-agent researcher example again.
Right. They found that splitting the task across multiple agents, each with its own focused context, significantly outperformed a single monolithic agent trying to juggle everything.
Why? Just because the individual context windows were less cluttered.
Pretty much. Each subagent could focus on its narrower, more manageable subtask without being distracted by context from other parts of the overall problem.
Makes sense. But there are downsides, aren't there?
Oh yeah. Multi-agent systems come with costs. Anthropic themselves noted their system could use up to 15 times more tokens than a single agent.
Wow, 15x. Why so much?
All the communication overhead, agents talking to each other, passing information back and forth, the coordinating agent trying to manage things,
Yeah.
it adds up tokens fast.
So you need really careful prompt engineering.
Extremely careful. You need robust strategies for coordinating the agents, managing the handoffs, making sure they share just enough context without overwhelming each other. Otherwise, you're just paying way more for potentially more confusion.
Okay, so breaking things into separate agents is one way to isolate. Are there other architectural patterns?
Absolutely. Environment-based isolation is a really interesting alternative.
Environment-based?
Yeah, look at Hugging Face's Deep Researcher agent. It's fascinating. Instead of having tool calls that return, say, big chunks of JSON data back to the LLM,
Uh-huh.
they use a code agent. This
Wow.
agent actually outputs Python code, which then gets executed in a separate sandboxed environment.
Whoa. So the LLM isn't directly handling bulky data objects.
Exactly. It isolates those token-heavy objects from the LLM's context window. As Hugging Face points out, if the agent needs to, say, download an image or process audio and store it for later, it just assigns it to a variable in the sandbox environment state. The data lives there outside the LLM's context, but the agent can still access and manipulate it later via code execution.
That is really clever. It keeps the LM focused purely on reasoning and code generation, not on being a data store.
Precisely. It leverages the execution environment for state management.
Brilliant. Okay, and then there's state-based isolation. You mentioned this earlier with scratchpads, but it sounds like it could be more general.
It's probably the most flexible approach overall. Here, you deliberately design your agent's internal state schema, the data structure holding its memory and current status to isolate different types of context into different fields.
And then you only show the LLM certain field.
Exactly. At each reasoning step, you consciously decide which parts of the agent state are actually relevant and expose only those specific fields to the LLM's context window. The rest remains hidden, but still available internally until needed.
Okay, that sounds like it enables a really advanced pattern.
Okay.
Maybe call it context partitioning.
That's a great term for it. Yeah. You can design your agent system so different parts, maybe different nodes in an agent graph, only get to see the specific slices of state they need.
So like a reasoning node sees conversation history.
Right. A tool-using node might only see the current task instruction and relevant data snippets. A planning node might only see the high-level objectives. A memory access node might see historical patterns.
But none of them necessarily see everything all the time.
Precisely. And the beauty is you can route information through the structured state between nodes without it ever needing to enter the LLM's context window unless it's absolutely required for a specific reasoning step.
That sounds incredibly powerful for managing complex flows.
Yeah.
And tools like E2B, the sandbox environments, they must amplify this.
Hugely.
Yeah.
Because they let you execute code in these isolated environments, you can persist really complex state like data frames, files, network connections externally in the sandbox while the agent maintains access to it via code, keeping the LLM's context clean.
So the big architectural takeaway here seems almost backwards from how people often start.
It really is. Many engineers dive into coding the agent's logic first, then they hit context walls and try to patch it.
Right.
But the teams building agents that actually scale, they've learned you have to design your context flow first, before you write the core logic.
Map out the information needs.
Yeah, map out what information needs to be available when and to which component. Then architect your agent's state, its memory systems, and its execution environment around that flow. It's foundational.
So for you listening,
Mm-hmm.
have you experimented more with multi-agent setups or trying to make single, very state-aware agents work? What trade-offs felt biggest to you?
I think that coordination overhead in multi-agent systems is often the first big hurdle people feel.
Yeah, definitely.
Okay.
Okay, this is all incredibly powerful conceptually. Write, select, compress, isolate. But how do you actually do this? Let's talk practical implementation.
Mhm.
How does a framework like, say, LangGraph help us put these strategies into practice?
LangGraph is really well suited for this because it's built around the idea of managing state explicitly in a graph. So for writing context,
Yeah.
it has built-in short-term memory essentially through its checkpointing system.
Hmm.
The agent's entire state automatically persists between steps in the graph. And it also has clear patterns and integrations for adding long-term memory persistence across sessions.
Okay, so writing is covered. What about selecting context?
LangGraph's state-based nature gives you that fine-grained control we talked about. Each node in your graph receives the current state, and you decide exactly what parts of that state to use or pass to the LLM. Plus, there are integrations for doing embedding-based retrieval over memory collections you store in the state.
Ah, so RG on your memories.
Exactly. And libraries like BigTool can help with that semantic search over tool descriptions we mentioned, making tool selection smarter.
Nice. And compressing context.
LangGraph has built-in utilities for common things like message summarization or simple trimming based on token count or message count. But critically, because it's just Python code in your nodes, you have total flexibility to plug in your own custom compression logic anywhere you need it. You're not locked in.
Good. That flexibility is key. And finally, isolating context.
Well, the whole state schema design is how you achieve state-based isolation and partitioning. LangGraph encourages that structured state. It also has direct support for integrations with sandbox environments like E2B.
For that environment-based isolation.
Exactly, and it works really well with multi-agent libraries like OpenAI Supervisor or the broader swarm concepts, making it easier to build those complex distributed agent systems where context is naturally separated.
And crucially, you need to see what's going on under the hood.
Yeah.
Observability must be vital.
Oh, absolutely essential. You can't engineer context effectively if you can't see it. That's where Langsmith comes in.
Right.
It lets you visualize the graph execution, track the state changes, see exactly how many tokens are being used at each step, trace how context is flowing or getting stuck, and really importantly, evaluate the impact of any changes you make to your context engineering strategies.
So the whole development loop becomes much clearer.
Yeah, it's iterative. You use Langsmith to trace behavior, spot a context bottleneck, maybe the history gets too long, or retrieval pulls in junk. Then you implement a targeted fix using one of these strategies, add summarization, refine retrieval, partition state. Then you evaluate the change using Langsmith again. Did it help? Did it break something else? And you iterate.
Okay, so the big takeaway then is crystal clear. Context engineering isn't some advanced technique you bolt on later if you have time.
No way. It's a fundamental architectural concern. It needs to influence how you design your agent right from day one, especially if you have any ambition for it to handle tasks that last more than a couple of turns.
Let's wrap this up then. Remember this key idea, that huge gap between AI agents that look cool in a short demo and those that actually deliver reliable results in real-world, long-running tasks. It almost always comes down to systematic context engineering.
It's not just about smarter prompts or waiting for the next bigger LLM. It's about smart architectural design for coherent, scalable reasoning over time.
And the teams building the agents that are genuinely starting to transform how work gets done. You know, the Anthropic, the OpenAI, the Cognition AI, the Hugging Face teams, they are all using variations of these patterns we've discussed, right? Select, compress, isolate.
And now you have that same conceptual toolkit they've painstakingly developed.
So here's a thought to leave you with. Context engineering is rapidly becoming as fundamental to building robust, scalable AI systems as memory management, garbage collection, and caching are to traditional systems programming.
That's a great analogy. Master it, and you'll build agents that can actually scale and maintain coherence. Ignore it.
You'll keep hitting frustrating walls that no amount of clever prompting alone is going to solve for you.
Next time on our deep dive, we're tackling something closely related: Agent evaluation at scale. Testing AI systems that think. How do you actually know if your complex agent is working correctly beyond just simple accuracy metrics?
It's going to be fascinating. Until then, think about your context flows. Design your memory systems deliberately, and remember this. Great agents aren't just smart, they're architecturally sound.